So the ONT instruments are actually generating longer reads and more of them. All right, and there are actually a number of long read assembly algorithms out there employing different paradigms. So unlike the short read assemblers, for the most part, utilizing the brain graph approaches, long reads are more, I guess, at some level, interesting to work with. One of the first is from Ruan and Lee, WT-DBG2, also known as the red bean assembler. I guess it was quite difficult to roll out the tongue, so they rebranded that as red bean, and it is based on an overlap layout consensus approach with fuzzy doubling graphs, where they segment reads into a 256 base pair tiles, and then they build a dynamic programming matrix to perform all versus all Smith-Waterman alignments to build some graph, and then they process that graph to build their consensus assembly. And there is the FLY algorithm from Tesner group, where they cluster reads from a given genomic loci, and they construct repeat graphs, align reads to the graph, and resolve the bridged and the near repeats to assemble their genome. And finally, there is the Shasta. In their tour de force paper, they assembled a number of 11 human genomes using this approach, where they actually have a reduced representation of their reads using mid-hash markers. And using those markers, they identify read-to-read overlaps. They build an alignment graph. They simplify those alignment graphs, like cutting these spurious links, and they perform some polishing and consensus calling to generate the underlying genome. Now, we take a different approach here. The GoldRush algorithm actually is based on the premise of the long read technologies getting better and better. So we would love to have one day these genome sequencers actually generating genomes, right? So in one go, you have the full 23 chromosome glory of the human genome, for example, right? So the problem that we wanted to solve, harking back at the Human Genome Project and the approach that they use, we wanted to select golden path reads out of the many millions of reads or hundreds of millions of reads that are generated by these instruments. So if we select those golden path reads as a close to one-fold representative of the genome, then we can polish those, we can correct for some misassemblies, we can scaffold those further if we can, using some redundancy from the other reads. So then the question becomes, how do we select the golden path? So for that, we input the raw reads. We initialize a data structure called a multi-index Bloom filter, which I'm going to expand more on. And then we loop over the reads, and we gradually build our multi-index Bloom filter if the read content is not already seen in previous reads. All right. So the set of reads that are tracked in the multi-index Bloom filter then is going to give us our golden paths, and we can do some things with them. Now, many of you must be familiar with the structure of a regular Bloom filter, where we can perform set queries on a budget. And we have generalized the concept using a multi-index Bloom filter or a MyBF. All right. So in a MyBF, what we do is we not only record the ones and zeros, but we record some index. All right, and it saves us some space. Now, how much space does it save us? Now, ideally, you can record those reads in a hash table, which is going to have an O1 operation, and the search is also going to be constant time. The memory, however, is going to be proportional to the number of elements in your set, the key size, and the number of targets you have, right? And then you can make a key value associations, and it doesn't have any false positives, it doesn't have any false negatives, so life is beautiful if you can afford the memory. Now, you can do the same thing using a regular Bloom filter. Well, actually, n of those, capital N of those regular Bloom filters, but you would again pay some price on memory, and we wanted to optimize that using this MyBF idea, which is I guess logarithmically related to the number of targets as opposed to linearly. All right. Now it comes at a cost. It comes at the usual cost of having some false positives, but also some false negatives. All right. But those can be mitigated or controlled for, and we argue that it is worth the memory footprint gains that are realized. All right, so we also changed the regular structure of or the regular strategy of using a Bloom filter. So instead of using multiple hash functions, we are using multiple space seeds to represent a string of characters or sequences in this case. All right. So what that allows us to do is it allows us to perform queries that allow for some mismatches. All right. So if we allow for a mismatch, a missed space seed queries, the false positive rate of a MyBF database is going to be represented by this equation. So the inner side of this the summation is a binomial, all right, and it is modified by this multiplicative factor that is a function of SI, which is the relative frequency of a given index I. All right. So that is the false positive, overall false positive rate of a MyBF. All right. But we're not interested in this particular value per se. We are interested in whether or not a longer sequence actually is a hit to a given index. All right. So in bioinformatics, we don't usually look at set membership of a single k-mer, if you will, but the adjacent k-mers. All right. So if we look at some number of frames n, small n, and if we observe some m sub I with some index I, all right. So mi of those n entries are returning a hit to a particular index I, where I is running from 1 to capital N, and that would be the false positive rate specific to that particular index I out of those sliding window searches. Now, of course, you can argue that we are making multiple hypothesis testing here, so we correct for that using a simple Bonferroni correction. All right. Now, here's the beauty of using MyBF. You can overload it. All right, and you can even take it to the extreme case of 100% occupancy rate for a MyBF. So for a MyBF of 100% occupancy with 5 space seeds, if we interrogate 10 adjacent frames and see that 8 of them are hitting a particular index I, all right? Then plugging those values into these equations, and if we have, say, 10 equally likely indices, all right, our false positive rate, so our false discovery rate is going to be like 1.4%, and after Bonferroni correction, it is 14%. All right, so nothing to write home about it. But if we have more number of indices, all right, so let's say 100 equally likely index, the Bonferroni corrected p-value is going to collapse to the order of 10 to the minus 7, right? So that's good, right? And one of the frequent questions that we receive is how do we design those space seeds? And I'm going to quickly go through this. Don't sweat, all right? It is really difficult to build bad space seeds, all right? So any space seed is better than a corresponding k-mer if you are looking at the sensitivity versus FDR plane, right? Okay, so now how do we use these MyBFs in GoldRush? We go through our long reads, all right, and gradually build the MyBF, interrogating our reads one by one. If they are not in there, we put it in the MyBF, and we select them for the golden path. And if they are already in there, we just discard. And we also do some trimming to get rid of redundant representation of excessive overlaps between golden path reads. And that's a linear operation. So that's the secret sauce, if you will, in GoldRush. All right. Then for the insertion, we divide blocks. We divide reads into blocks of size B. All right. So that's the number of tiles in a given block, and then we record all read signatures inside the block using the same index. All right. So more indices, the better for MyBF. Up to a point, of course, you would still have to stay within the bounds of say a 16-bit integer or something like that. And then when we are querying the golden path, we look at our reads, and we select some representative ID from the query reads in the MyBF. So in this case, in a very simple strategy, we just select the highest count to be the representative ID. All right, and that way we can say, all right, given a read, after interrogating the MyBF, we have assigned these IDs 1115, 222, 2023, and with the associated counts. All right. And we threshold those counts to say if they are assigned or unassigned, right? If a tile is assigned true, then the tile is assumed to be found in the golden path, right? And then we insert those reads that we query into the MyBF if the assignments are false, or if the assignment is partial, we trim and insert. And if the assignment is true for those tiles, we skip those reads. All right. And then we go through the golden path reads to polish them. All right. So we have a protocol we published recently using anti-edit and sealer to go through those golden path reads to polish the micro misassemblies, if you will. So in the interest of time, I won't go to too much detail about NT-edit the Sealer pipeline, but I'll be happy to answer any questions on it. All right. Next, we look at the golden path, the Polish golden path reads to fix for misassemblies. Now, misassemblies can happen, especially for the ONT platform, when there are chimeric reads. All right. So if a read is chimeric, indicated like in this line, some part is gold, the other is blue. Even though that there are other pieces in the original assembly that we can actually contiguate these sequences, because of this this chimeric read, we cannot do scaffolding or further contiguing. All right. But if we cut those misassemblies, then we can rescaffold with the correct partners, right? So we have adapted the Pigment algorithm to work with ONT reads and PANGAIA reads too. Like we can discuss that if you would. All right. Next, we do some scaffolding. We use an idea similar to what was used in Stash. We represent we build a reduced representation of the reads using some minimizer sketches, all right? And we map those minimizers to the assembly that we have, to the Polish golden paths that we have, all right? So I'm using the word mapping as opposed to alignment. Mapping is a crude approximation of who belongs where, all right, as opposed to accounting for base by base, and that's mapping what we need for scaffolding here. And then using those mapping information, we can join links, detect overlaps, and we can use again a sealer to fill the gaps, and we can run this in an iterative way to build the longer context using the information that we gather throughout the process. All right, so some benchmarking results. We have tested GoldRush on a number of human genome cell lines and two plant genomes, a rice genome and a tomato genome. All these sequences have some fold coverage around 60 to 70 fold. And their read lengths are also compatible between 30 to 48, 49, and 50 length. And they were base called using various versions of Guppy. And their estimated error rates range between 4% to 20%. So 20% for rice, 4% for NA24385. So how do algorithms cope with such a variety of error rates was the question that we had. All right, so benchmark results on human genomes. GoldRush is aptly shown in gold. We compared its performance to Fly, the Red Bean, and Shasta. And we look at the performance of these algorithms on contiguity and correctness dimensions, as well as their resource usage in terms of peak memory and execution time. All right. We can see that for the human genomes, the performance on those three genomes for all four algorithms, they are more or less the same, although there may be some variability from algorithm to algorithm. And on this plot, the contiguity versus number of misassemblies, you would want to be on the top left corner, right? And for the resource usage, peak memory versus time, you would want to be at the bottom left corner. All right. So we can see that for some data sets, GoldRush is on the Pareto front, but not for all the data sets. It can have lower misassemblies, but in this particular test, the fly had the better contiguity. And for memory usage versus time, Shasta was the fastest one, but it required of the order of 900 to 1 terabyte, 900 gigs to 1 terabyte memory. And in terms of the overall performance of GoldRush on these 3 genomes, we can see that we are approaching a level where we can actually look at ideograms like this to identify how much of those genomes, of those chromosomes we put in a single piece or a few pieces, and the picture looks promising, and it can only get better with improving technology and algorithm as well. Now, of course, the other question is, you can look at the genic space. Here, I'm showing the BUSCO completeness for the human genome in a 24385. And GoldRush, Fly, Red Bean, and Shasta do have a range of complete BUSCOs. The lowest being the Red Bean assembler, and the highest being the Fly. And the GoldRush assembly here, this particular assembly was polished using anti-edit and sealer. Alternatively, we polished it using Racon to see that BUSCO completeness actually can be improved. All right. But of course, using Racon comes at a price, especially in peak memory usage. So it has orders of magnitude more computational resource demands compared to Gold Polish. All right. Finally, the plant genomes. How do we perform on plant genomes? Again, being on the top left is good for contiguity versus misassembly, and the bottom left is good for resource usage. I think we have some clear winners for tomato. And for rice, the story is a little more complicated. And for peak memory usage, the GoldRush is sitting down below, and the time complexity is again quite scaling quite nicely. All right, with that, I'll acknowledge my collaborators on the project. These are people in my group who actually did the grunt work, and I'm just the mouthpiece here. You can find the GoldRush on our GitHub repository, and the project I described today was partially funded by Genome British Columbia, Genome Canada, and the National Institutes of Health of US. So with that, I thank you for your attention. I'll be happy to answer any questions you may have.
Thank you very much for this talk. And we already have a question, but I do not see who is asking to speak. So feel free to take the scene if you want to speak, to ask a question.
Okay, so excuse me. Yeah, hello, Inanc. Thank you for this great talk. I'm very happy because I suggested you because I read this paper out of interest out of other interests earlier. Is it maybe fair to say that, well, your method, I tried to summarize the achievement. your method is you can now assemble even like very complex and long genomes on a laptop, if you want. And this is now the first method that makes it possible to do this. And the major application that is supported is if you would like to compute a consensus assembly of the reads that you have in front of you on your laptop, but not necessarily really going into the diversity of haplotypes that populate the read, kind of, or give rise to the reads, right? Which still, it's an excellent starting point. If you have this first genome, you can work with this, and you made it on a laptop. So this is like the idea that came to my mind, and I was interested in that idea for certain reasons. This is why I suggested you as a speaker.
So we're talking about the phased assemblies, right?
Yeah.
For diploid genomes. Yeah, for sure. So the workflow currently does not assemble phased assemblies. But it has a collapsed diploid assembly with a haploid representation, right?
Mm.
So we do have some work plans to actually leverage what is coming out of GoldRush to build those haploid assemblies, but it's still a work in progress at the moment.
Okay, thank you. Thanks.
Paola?
Hello, thanks for the very nice talk. My question is about possible extension of GoldRush. Do you think it could be some of the techniques used even for metagenomics assembly from nanopore data?
Thank you for that question. Actually, I'm on sabbatical in Ankara at the moment, and that was one of the term projects that I had assigned to one of my students. All right, and what the task was to actually play with the parameters. So blindly taking GoldRush as a black box. All right, playing with the parameters of the algorithm to measure its performance in assembling metagenomes. So we are still trying to understand why it is working for certain data sets better than others. But yes, it does have some competitive performance to MetaFly.
Thanks, that was my question. Compared to MetaFly, how it could work. Thanks. Thanks again.
I have a small question about running time. So if I understood correctly, on your paper, GoldRush is, say, 4 times slower than Shasta on human genomes. Do you know what takes time in the pipeline, and if we could think of some improvements?
Right. So compared to Shasta, right?
Yeah.
Yes. The majority of the time spent was on polishing the assemblies, right? Now that would require building up gold polish, and what we are working on right now is a machine learning algorithm swapping for the rule-based algorithm that we have in GoldEdit or gold polish. So I think machine learning has a role to play in both making those assembly corrections better and faster. It is the I guess training time can be amortized or parallelized, if you will, with the earlier stages of the assembly. So yes, there's some room for growth for sure, and that's where we are concentrating on at the moment.
Mm-hmm. So finally, this means that the first step of creating a kind of draft genome is something that is achieved, but the real difficulty is all the rest in polishing and splitting errors and so on, right?
That's right. Yeah. And being able to do that in a budget, in a budget for computational resources.
Mm-hmm.
So yeah, I think it is fair to say that, for example, when link-read technologies, say from 10x Genomics, was in the works, there were some algorithms that were able to assemble complex genomes, but it took exuberant amounts of memory and long execution times. And if we want to employ these algorithms, say for cancer genomics, which is the bread and butter at our center, we have to be able to do these in timelines using resources that can be compatible with healthcare, right? So that's what we are striving for.
Okay, thanks. Next question. I saw someone who raised his hand, but I don't know who it is. Can you see it? I don't know. And I had, if there is no other, I had a small technical question. So you mentioned that GoldRush created something close to 1x coverage of the genome. Does that mean that you need to know the size of the genome prior to the computation, or is that something that is not the case?
You don't have to.
Okay.
Because the construction of MyBF is going to take care of that, right? So the genome size is not an input to the MyBF. Having said that, to set the size, to set the memory footprint of MyBF, it would be useful to have a rough estimate of how much sequence we're talking about, right? And there are algorithms like NT-card, for example, that can do that in a matter of seconds. So given a data set, if you were to run NT-card, it will give you an idea about the genome size in a matter of seconds.
And if you have very long repeats, like longer than reads in the input data sets, the GoldRush algorithm will collapse them, and then you have to duplicate them at the final steps?
Absolutely. The repeats, as always, are going to throw a curveball at you, right? And so of course the schematic that I showed here is a very simplified version, right? So what if you had the flanks returning true and the middle section returning false, or if you had the true in the middle and false at the flanks, right? So those can be thought of as some repeats. Like if the flanks are true and the middle is false, it can be interpreted as you are coming in from a repeat sequence, going into a unique region, exiting at a repeat, which is quite bad for assembly, but you can trim and preserve the middle section, right? And if you had a false at the flanks and true in the middle, you actually have a resolved repeat, right? So it would make sense to record the entirety of that read in your golden path, and that's what we do, and that's what I somewhat cryptically alluded to when I said with improving sequencing technologies, the GoldRush algorithm performance should improve, right? Because at some level, in some not so distant future, I'm hoping, it would be a matter of selecting reads that represent the complete chromosomes or chromosome arms, right?
Yeah. Do we have some other questions anywhere on Earth? So if not, I would like to again thank you.
Well, thank you very much for the opportunity and the great questions. So we are still working on the algorithm. So we're hoping we're going to have some updates on it in some conferences or some follow-up publications, hopefully. All right, and looking forward to further interactions with the group.
With great pleasure. And have a nice day, everyone.
Yeah,
See you later.
it's another time also for me.
Thanks.
Thank you very much. Yes.
Bye,
Bye.
Paul.
Bye-bye.
Bye now.